Good morning. All right, so we're going to pick up where we left off. 3.6, we've got two more examples to finish up there, and then I'm going to move into 3.7 today. There's only really two examples I need to do in that section, so hopefully we can finish all of that up today. Again, tomorrow then will be a review day, and then as soon as we come back from the break, that's when the test will be posted, because again, I'm not going to obviously post it tomorrow and have it due over Easter or anything like that. So I'll post it as soon as we come back on Wednesday of next week. It'll be due at the end of next week by Friday at midnight. Okay, so that's our plan for now. Again, make sure that you're working on the 3.6 and 3.7 homework though, because those are due. Let me just double check. I have those due by Thursday, which is tomorrow, right? So we'll finish up 3.7 today. So make sure you're working on that so that you can finish up that homework before the break. And that way you can just focus on the test when we come back, okay? Any questions, comments, concerns before we get started now? All right, so let's take a look here at example 8. So it says to graph. What we're going to do is what we did in the previous examples, where we're going to look for any vertical asymptotes, horizontal asymptotes, right? And then we'll talk about domain and range and think about what the graph looks like. Because again, I know you're going to have access to either a graphing calculator or Desmos on your test, so you can obviously put these in there. Those are the types of things I'm going to be asking for is, can you calculate all the pieces, right? So let's see if we can do that here. Now, what was the first thing we said we always want to do if we're looking for the domain and range and the vertical and horizontal asymptotes? So what's our first step to be able to find those asymptotes? Good. We need to factor first, right? So let's take a look at what we've got here. Is there anything we can do with the numerator this time? No, right? X minus 3 already as simplified as it's going to get, so we'll keep that. And now let's look at the denominator. How would you factor the denominator? Good. We have a common factor of x, so we can factor that out. So we're going to have x times x minus 3 this time. Now, always look to see if you have any common factors. Do we have any common factors this time? We do, right? So remember, if you have a common factor in numerator and denominator, we can actually cancel those out. So if we cancel the x minus 3, what's going to be left then? What's this function going to look like? Okay, so be careful though. The x is in the denominator, right? So it's not going to just be x, it's going to be what? 1 over x, right? So we're going to keep a 1 in the numerator and keep the x in the denominator. So that's how this function is actually going to simplify this time. Now, if we're looking for our vertical asymptotes then, how would you find vertical asymptotes for this function? Think about what we did on those previous examples when we were looking for vertical asymptotes. We set the denominator equal to 0, right? So what are we going to set equal to 0 this time? Just x, right? So this is going to be x equals 0, which is already solved. That is our vertical asymptote now. Okay, so that's why it's so important now to factor first, see if there's any common factors, because if any of them cancel out, we're only going to look at whatever's left in that denominator at the very end and set that equal to 0. So our only vertical asymptote this time is x equals 0. Now, let's think about domain. If I want to know the domain of this function, I can't just look at the vertical asymptote this time, because the previous step has an extra factor in it, right? And that was technically part of the original function. So there's actually going to be an additional restriction on my domain that does not show up in my asymptotes. So when I find my domain now, I'm going to take x can't be equal to 0 and x minus 3 can't be equal to 0. So we already know there's a restriction at 0 because that's our vertical asymptote. What's the other restriction going to be? Three, right? So x not be equal to positive 3, because there I'm just going to add 3 to both sides, so we get that. So now if we actually write our domain with those two restrictions, what's the domain going to be this time? Using interval notation, sorry. Good, negative infinity to 0. We have our union. We're going to go from 0 to 3. Have another union, and then we're going to go from 3 to infinity. So again, don't just assume that your vertical asymptotes are the only restrictions on your domain, right? If you had a factor in the denominator that happened to cancel out, it's still a restriction on the domain, because if you go back to the original function and you plug in 3, it's going to give you 0 in the denominator. So we have to remember that. But in terms of the vertical asymptotes now, we only look at the final answer and set that denominator equal to 0 to find the vertical asymptotes. We're going to look at the graph of this so you can see exactly how all this shows up. If you have any questions right now on finding the vertical asymptote and the domain for that one? Okay. Now, what about the horizontal asymptote? How would you find the horizontal asymptote this time? Okay, so let's think about it, right? We know it's one of those three situations, right? So let's look at our degrees first. What's the degree in the numerator this time? 1, right? Because there's an understood 1 here on x to the first power. The degree in the denominator is what? Okay, and so we said if the degree in the numerator is smaller than the degree in the denominator, what does that mean? It's always going to be y equals 0. Okay, so this one right here should have a horizontal asymptote at y equals 0. So only do the leading coefficients if they're the same degree, right? In this case, the degree up top is smaller than the degree on the bottom. Therefore, it's automatically just y equals 0 in this case. Any questions on that one now? We'll talk about range when we look at the graph, right? I'm probably not going to ask for range on a test anyway. It's mostly going to be domain, finding those asymptotes. That's right. Only divide the leading coefficients if the degree is the same on the top and the bottom. Right? That's the only time we would do that to find the horizontal asymptote. Okay. If the numerator is bigger than the denominator, that's what we're going to look at on, well, the next example, right? And then we're also going to do an example 9 that says, what if the degree is exactly 1 bigger than the denominator? Then we have another type of asymptote that we have to look for. Okay, so we're going to look at that on the next ones. Okay, all right, so let's take a look at this graph, right, just so we can see how all this stuff actually shows up now. All right, so we have y equals x minus 3 over x squared minus 3x. Notice here, when we simplified, we got 1 over x. And if you remember, way back to the very beginning of this section, 1 over x is our basic rational function, and this is what it looked like, right? So simplifying this one gives us that. Now we said we should have a horizontal asymptote at y equals 0. X-axis, there's that blue line, that's our horizontal asymptote. We also should have a vertical asymptote at x equals 0, that's that green line. Okay, so that's correct. And remember we said our domain, though, does not include positive 3. And so if you trace along here now, see if I can get right on 3. Of course, it's jumping around 3. I can't see it. There it is. Okay, so you can see there at 3, it says undefined. Okay, and so what actually happens is we have a hole in our graph, an open circle in our graph at 3, because substituting 3 would make the function undefined. But again, it's not an asymptote because that factor actually cancels out now. So any factors that cancel out are still restrictions on the domain, but they're not going to show up as asymptotes. They're going to show up as holes instead. Okay, so that's what that graph would look like. Any questions on that now? And again, if you wanted to know the range, right, it would go from negative infinity to 0, 0 to infinity, because it does not go through that horizontal asymptote this time. That's right. If you have a factor that's in the numerator and denominator, then you're going to get a hole at that location. That'll be all the time. Any factor that cancels out gives you a hole in your graph now. Any other questions there? All right, so let's take a look at this next one now. All right, so again, what's our first step going to be this time? Good, so let's factor the numerator. What can we factor in the numerator this time? Yeah, we have an x squared, so we're going to have x squared times, and that's going to leave us with x minus 2. And then x minus 2 in the denominator, we can't do anything with that. Now, if we simplify this, what's that going to give us then? Just x squared, right? Because the x minus 2's cancel out. The x squared's in the numerator. So this just becomes x squared this time. Any questions about that? All right, now let's talk about our vertical asymptotes. If we look at this, remember we look at the final answer this time. What vertical asymptotes are we going to have? Okay. So not x equals 2 because the x minus 2 factor canceled out, right? We only look, there are none. There is no denominator in our final answer this time. So we would say in this case that there are no vertical asymptotes. So if all of your factors cancel out and you're not left with a denominator at all, then there aren't going to be any vertical asymptotes anymore. Okay, it can't be 1, right? Because in this case, if you wanted to put this over 1, there's no x to substitute a 1 in there, right? It's just a 1 by itself in the denominator. So you're looking for what would x have to be to make that undefined. There's nothing I could put in there to make that undefined now because it's just x squared. All right, so yeah, so this, since there is technically no denominator there, no x in the denominator, no vertical asymptote. Okay. What about horizontal asymptote? None, right? So this is one of those cases. Notice here we have a 3 as our degree in the numerator, a 1 is the degree in the denominator. If the degree in the numerator is bigger than the degree in the denominator, then we just say there are no horizontal asymptotes. Right. Now, what about domain this time? Okay. Now, be careful because remember on the previous one, we didn't look just at the final answer. We had to go back before we canceled anything out. That's right. 2 is still going to be a restriction on the domain, right? So x minus 2 is in the original function. So that can't be equal to 0 because that would give us 0 in the denominator. So x can't be equal to 2. So our domain is from negative infinity to 2 and 2 to infinity. And so what's going to happen at 2 then on our graph? It's a hole, right? Okay, so there are no vertical asymptotes this time, but we are going to have a hole at 2. So what will this graph look like if we got x squared as our final answer here? It's a parabola, right? Okay, so we're going to have that U-shaped graph. Rather than switching to Desmos, I'm just going to sketch it over here. Okay, and over here at 2 now, we're going to have a hole. So you're going to have something that looks like this. So since it's simplified down to x squared, it is that parabola with a vertex at the origin. And the only thing we have to worry about is the fact that 2 is not included. And so you do have a hole at x equals 2 this time. Any questions on that one now? All right, let's take a look at this one now. So this time we've got x squared minus 4x minus 5 over x minus 3. What's the first thing we want to do here? We're going to try to find all those same things we're looking for. So let's factor, right? So what would our factors be for that numerator? Good, x minus 5 and x plus 1. All right. Do we have any common factors this time? No, right? So nothing cancels out. All right, so let's start going through our list of things to find. Let's look for vertical asymptotes first. So where are we going to have a vertical asymptote this time? At 3, right? So remember, we can take the denominator, x minus 3, set it equal to 0. It's going to give us x equals 3. And remember, for vertical asymptotes and horizontal, always put the actual equation. So in this case, vertical asymptote would be x equals 3. Now, what about horizontal asymptote? There are none, right? Because again, we would look at our degree up top, that's a 2. Degree in the denominator is 1. If the degree in the numerator is bigger than the degree in the denominator, we can automatically say there are no horizontal asymptotes. Now, what about our domain this time? Everything but 3. Good. So no x 3 can't be equal to 0. That's going to say that x can't be 3. We're going to go from negative infinity to 3 and from 3 to infinity. Okay. So our vertical asymptote is the only restriction this time. All right. Now, here's what we got. Here's the new piece. If we don't have a horizontal asymptote, and if the degree of the numerator is 1 bigger than the degree of the denominator, so in this case we have a 2 in the numerator, we have a 1 in the denominator, 2 is 1 bigger than 1, then we actually have what's called a slant asymptote for our graph. So the only time we even have to check for this is if there are no horizontal asymptotes. If there's a horizontal, there's not going to be a slant, you don't have to do this. Okay, but if there's not a horizontal, look at those exponents, see if the top is 1 bigger than the bottom, and if it is, we need to look for a slant asymptote. The way we're going to find the slant asymptote is by using long division now. So I'm actually going to divide the numerator by the denominator. I'm going to put my x minus 3 on the outside. I'm going to put the x squared minus 4x minus 5 on the inside. Now, you might be saying, well, in this one, couldn't you just do synthetic because you have x minus 3 as your factor? Technically, yes, right? But I'm going to do it as long division because sometimes that denominator is going to have an exponent other than 1. And so this will always work, right? So if you have something other than just a linear factor in the denominator, we have to use long division in those cases. All right, so let's review our long division now. What's our first step for long division? Okay, good. So we look at the first term x squared, the first term x, right? First term on the inside and outside, divide those. Well, what's x squared divided by x? X, good. So I'm going to put my x up top. Then remember we distribute to everything on the outside. So we have x times x squared, that's going to give us an x squared. Then we have x times negative 3, that's going to be a negative 3x. Okay, once we get that, then what do? Subtract, good. Subtracting this now. Well, x squared minus x squared, that should cancel out. What's negative 4x minus a negative 3x going to give us? Okay, so almost, right? So if we start with negative 4x, then it becomes plus 3x, right? What's negative 4x plus 3x? Negative x, good. Negative x. Then we can bring down the next term, which is a minus 5. All right. What's our next step going to be? Okay, good. So we're dividing, again, the first term by the first term. Our first term down at the bottom now is negative x, dividing by the x on the outside. So that's going to give us what? Negative 1, good. That goes up top. And now we distribute. Negative 1 times x, negative x. Negative 1 times negative 3 becomes a positive 3. And then we're going to subtract again. Group all that together and subtract. And if we do that, what should we get? Okay, so we have -5, and then it's technically a -3, right? So that actually give us what? -8, right? Excuse me. Right? Now, at that point, can we divide any more? No, right? -8 is not divisible by x, so we're going to stop right there. That's our remainder. But in this case, for our slant asymptote, all we really care about is the quotient. So it really doesn't matter what that remainder is. We only care about what's up here at the top now. So in terms of our slant asymptote, it's an equation. So it's going to be y equals, and then it's going to be x minus 1. So what that tells us now is that we actually have a slanted line that our graph is approaching as we go to infinity and negative infinity. So instead of just having a horizontal line like y equals 2 or y equals -5, things like that, now there's actually a slanted line, and we're actually approaching that line instead. Any questions on finding that slant asymptote now? All right, so let's look at the graph because I want to show you what this actually looks like when we graph it. All right, so y equals, numerator was x squared minus 4x minus 5. Denominator was x minus 3. That's what our graph looks like this time. So we already said vertical asymptote should have been x equals 3, right? So there's the black line. You can see that if you want to zoom out a little bit, just so you can kind of see that it is approaching that vertical asymptote from the left and the right this time. We said there are no horizontal asymptotes, right? And you can kind of see that on the graph, right? There's no horizontal line that as we go to infinity and negative infinity, we're not approaching that. But we said there should be a slant asymptote now at y equals x minus 1. Okay, so if I graph that line, there it is. And you can see now that red line, the blue curve, as I go towards negative infinity to the left, I'm approaching that line. And as I go towards positive infinity to the right, I'm also approaching that line. And so that's why we call that a slant asymptote for this curve now. So like I said, to know that there's one without actually looking at the graph, if the degree of the numerator is 1 bigger than the degree of the denominator, that's when we need to find a slant asymptote. Because when we do that long division, it's going to give you a line, a linear equation, and so that's going to be your slant asymptote in that case. Again, the only time you even have to worry about is if there's no horizontal, right? Because if there's a horizontal asymptote, there's not going to be a slant asymptote. Any other questions there? All right. So that's it for that section. So we're going to move on to our last section for chapter 3. All right. So 3.7, polynomial and rational inequalities. So now we're going to look at some polynomial functions and rational functions. We're going to think of them in terms of inequalities instead of equations now, and actually find some solutions to these inequalities. Okay, so the first one we're going to do here, example 1, we have a nonlinear inequality, right? So it's polynomial because we have that 2x cubed plus x squared plus 6 greater than or equal to 13x. The first thing we're going to want to do with this one is to move everything to one side. And that's always going to be the case when you have any non-linear inequality, right? Anything that's not just x greater than 2 or something like that. Always move everything to one side, get 0 by itself. Okay, so I'm going to subtract the 13x this time, which is going to give us 2x cubed plus x squared minus 13x plus 6 greater than or equal to 0. Now, we did some similar to this all the way back in chapter 1. We just didn't do them with higher order polynomials. The highest we went was quadratic with an x squared in it. So now we can actually do things with polynomials that have degrees bigger than 2. All right, now, once I've got everything to one side, what do you think our next step might be here? We need to factor. Good. So if we look at this one now, what are we going to have to do to factor it? We need our P's and Q's, right? Now, what I'm going to tell you here, just for the sake of time, because I do have another example I want to make sure we get to. This example we've already done back in section 3.4. This was example 2. So if you go back to section 3.4, example 2, we already did our P's and Q's for this, right? And we already figured out what the factors are going to be, right? So that's what I'm going to use is what we already found. So this actually works out to x minus 2 times 2x minus 1 times x plus 3. Okay, so rather than taking the time to go through the P's and Q's and all that again, if you just go back and look at section 3.4, example 2, we did all that work already. Okay. Now, once we have the factored form, now we're going to take each one of those factors, we're going to set it equal to 0. So even though this is a greater than or equal to 0, right, we need to set each factor equal to 0 now. So x minus 2 equals 0, 2x minus 1 equals 0, and x plus 3 equals 0. So what's that going to give us then for our x values if we solve each one of those now? Good, right? So we have x equals 2 here. This one we would add the 1 and divide by 2, so we get 1/2. And then this one over here, we're just going to subtract 3 and get negative 3. Now, if you remember back to chapter 1 with these inequalities, once we actually know what those values are, now we're going to create a number line so that we can actually choose some test points to see where this thing is positive and negative. I'm going to draw my number line now. Smallest value we have is negative 3. Next value would be 1/2. And our biggest value is 2. So we factor first, right? Use your P's and Q's if you need to do that. And then once we have the factors, we set them equal to 0, find the values for our number line, and now we're just going to put those points on the number line. Now I'm going to choose a value in each of my intervals to figure out where this thing's positive and negative. What's a value that I could use in that first interval that's less than negative 3 now? Negative 4 works, okay? So anything that's less than negative 3 is okay there. I'm going to substitute that into my factored form now. So I'm going to come back up here to see if this thing is positive or negative. So I'm going to do negative 4 minus 2, 2 times negative 4 minus 1, and then negative 4 plus 3. Now, all I care about is whether this is positive or negative, right? So I really only care about the signs here. -4 minus 2, is that going to give us a positive or a negative? It's going to be negative, right? So that gives us a negative. Then we have 2 times -4, which is -8, minus 1. Is that going to be positive or negative? That's also going to be negative. And then we have -4 plus 3. Is that going to be positive or negative? That's going to be negative. We end up with 3 negatives this time when we substitute in the -4. Well, if I multiply 3 negatives together, is that answer going to be positive or negative? Negative. Anytime you multiply an odd number of negatives, you're going to get a negative value. So that tells me everything in this interval down here now is negative. Any questions about how I got that? All right, what's the value between -3 and 1/2 then? 0 works, right? That's going to be the easiest one. So again, I'm just going to plug into that factored form. We're going to have 0 minus 2, 2 times 0 minus 1, and 0 plus 3. Again, all I care about are the signs. Is 0 minus 2 positive or negative? Negative. 2 times 0 minus 1, positive or negative? Negative. And 0 plus 3, positive or negative? That one's going to be positive. So this time I've got 2 negatives and a positive. So when I multiply all of that together, what should I get? That one's going to be positive, right? Because we have an even number of negatives this time. So that should come out positive. Now we need something in the interval between 1/2 and 2. What value could we use there? 1 works. We'll do 1 minus 2, 2 times 1 minus 1, and 1 plus 3. All right, 1 minus 2, positive or negative? That one's negative. 2 times 1 minus 1, positive or negative? That one's going to be positive. And then 1 plus 3 is positive. So overall, this one should be negative. Good. We only have 1 negative. That's an odd number of negatives. So that should be negative overall. And finally, we need something bigger than 2. What can we use there? 3 works. Now we have 3 minus 2, 2 times 3 minus 1, and 3 plus 3. 3 minus 2, positive or negative? Positive. 2 times 3 minus 1 is positive, and 3 plus 3 is positive. Good. 3 positives will give us a positive overall. Perfect. Any questions about how I found those signs now? All right, now, do we care about positives or negatives this time? We want the positives, right? Because we want this to be greater than or equal to 0. So we come back up here, right? Well, technically, I guess it's the next step once we've already set it greater than or equal to 0. Okay, so that's the sign we're looking at. So I only care about positive values this time. So now we just need to write our intervals and we're done. So what would that first interval look like this time? Good. So -3 to 1/2, Notice this time I'm using brackets because it could be greater than or equal to 0. The -3 and the +1/2 would make it equal 0, and so I'm including those values. Then I'm going to have a union, and then what's my other interval going to be? Two to infinity. Good. So bracket 2 to infinity, again, including the 2, because 2 would make it equal 0, and so I want to include that value. And so this right here is our solution to that inequality now. So again, move everything to one side, get 0 on one side, factor, use P's and Q's if you have to, get those values for your number line, substitute values in each interval, figure out if it's positive or negative. In this case, because it was greater than or equal to, that's why we chose the positives. If it was less than or equal to, then you would have chosen the negative intervals instead. That'd be the only difference there. Okay? Any questions on that one? All right. Example 3 is the last one we're going to do. This process is pretty much the same. When you say pretty much the same as what? What we already did in chapter 1? Yeah, right? It's identical. The only difference, like I said now, is we've got some polynomials that have higher degrees to them that we can actually find the factors, whereas back then we only knew how to factor quadratics, and so we could only work with x squares, right? So now we can actually work with things that have 3, 4, even 5 zeros and find all of those intervals now. Okay, but yeah, this overall is still the same. Good. All right. So now we want to solve this rational inequality. So again, first step, it's nonlinear, so we still want to set this greater than or equal to 0, right? So I want to move everything to one side first. So my first step is to move the 1 over. We're going to have 1 minus 2x over x squared minus 2x minus 3 minus the 1 greater than or equal to 0. All right, now, we've done one with fractions like this before. Does anybody remember what the next step would be here to actually start to solve this? Okay, so before we factor, we've got to do something else first, right? Eventually we need a common denominator because we need to be able to put all this stuff together first before we factor it, okay? So in this case, we know the 1 could just be written as 1 over itself, right? So its common denominator is just going to be this thing right here. We're going to have 1 minus 2x over x squared minus 2x minus 3. And then this is just going to be x squared minus 2x minus 3 over x squared minus 2x minus 3. Because that over itself would give us 1. Any questions about finding the common denominator for this one now? All right, now let's put these two fractions together. So if I subtract here, what am I going to end up with in the numerator? Almost, right? So be careful here. We're subtracting everything in that numerator on the right here. The negative 2x minus negative 2x, that becomes a plus, so those cancel out. But then we have a 1 minus a negative 3. So what's 1 minus negative 3 going to be? It's actually going to become 4, and then we're subtracting the x squared. So it's actually going to be a minus x squared now. Any questions about how I got that in the numerator? My denominator, again, is still just x squared minus 2x minus 3 greater than or equal to 0. So now I've combined everything into a single fraction. What's our next step going to be? Now we can factor. Good. How would we factor that numerator? Good, right? So it's a difference of squares. 2 and 2 would give us 4. X and x would give us x squared. One needs to be positive, one needs to be negative. Now, be careful here. Don't put x minus 2 and x plus 2. That's not the same thing. Okay, so it actually needs to be in this order since it was 4 minus x squared to begin with. So start with the 2's. Okay. What about the factors of the denominator? Okay, good. So we're going to have x minus 3 and x plus 1, because that would give us our negative 3 at the end. Negative 3x plus 1x would give us a negative 2x in the middle. Now, once we have our factors, we're going to do the exact same thing we did on the previous problem. We're going to set all those factors equal to 0. We're going to do our number line, and then we're going to choose our intervals. I'm going to do 2 plus x equals 0, 2 minus x equals 0, x minus 3 equals 0, and x plus 1 equals 0. All right, so what are the 4 values we're going to use on our number line this time then? Okay, so we get x equals negative 2 for this one. This one's going to give us x equals positive 2. We have x equals positive 3, and x equals negative 1. Okay, so now we do our number line. Make sure you put things in order. Negative 2 is the smallest. Negative 1 would come next. Then we have 2, and finally 3. So we got 5 different intervals to test. For the sake of time here, right, I'm going to tell you what values I would choose, right, and then I'm just going to tell you what the signs would be and where to substitute them in just so we have time to finish it out. So here I could use something like negative 3, something between negative 1 and negative 2, negative 1.5 would work, something between negative 1 and 2, 0 is the easy option, something between 2 and 3, we could use 2.5. And then something bigger than 3, anything bigger than 3 is fine. Now, we would come back to here to our factored form, and we would substitute those numbers in to see whether we get a positive or a negative. Okay, but if we do that here, this should give us a positive for this interval, negative for this interval, positive here, negative here, and positive down here. Sorry about that. I was looking at the wrong one. Switch that. Should be negative, positive, negative, positive, negative. Yep, that looks right. Okay, now, in this case, are we looking at positives or negatives? We want the positive values because, again, we want this to be greater than or equal to 0. So I'm looking at this interval and this interval this time. So now it's just a matter of writing those intervals. What's the first interval going to be this time? So we're going to go from -2 to -1. Now, be careful here. I agree that the -2 is included, but remember, -1 came from this factor in the denominator right here. If I put a -1 in there, it's actually going to make this thing undefined. We cannot include that value, right? So -1 not be included. So we're going to use parentheses on that one. What's our other interval going to look like? Good. 2 can be included. 3 cannot, because again, the 3 came from this factor here. So make sure you use a parentheses on the 3, bracket on the 2. And so this now would be our solution to that inequality. So I know we're out of time, so I'm going to let you go. If you have any questions, I'll hang out for a couple more minutes, though. Again, be working on the homework because that is due by midnight tomorrow night. Tomorrow we will review. And then when we come back from the break, then we'll actually have the test, which will be due on Friday of next week by midnight. Okay? Have a great afternoon, and I will see you all tomorrow.